Hello, welcome to our video to supplement section 4.7 with repeated eigenvalues. We've got an example of an initial value problem here because we didn't exactly do an initial value problem in class, and so the solving process is the same. It'll just be that final step, and so you get to see a whole other worked out example plus solving for C1, C2 because we do have a 2 by 2 here. So here is our system. We have our 2 by 2 matrix, and you can go ahead and find the determinant of this. It's actually pretty easy and straightforward. I'm going to go ahead and just say for this, if you do that, you will get a characteristic equation of lambda minus 1 squared equals 0. Okay, so make sure you know how to obviously do that. We're going to skip that step in this video. So we get a repeated eigenvalue of lambda equals 1. We're going to go ahead and figure out what to do when we plug that 1 in. So I get 2 minus 1 for this element, 0 minus 1 for that element, and everything else remaining the same. So you can see here, if I augment this with 0, 0 in order to solve, I get that row 2 is just a scalar multiple of row 1. Row 2 is just row 1 multiplied by negative 1. So really, my only help here would be from row 1, I get that x1 plus x2 has to equal 0. And if that's the case, then x1 has to equal the negative version, the opposite version of x2. So if I create an eigenvector for that fits that, x1, I could do 1 and negative 1 pretty easily for that, or negative 1, 1. Any other eigenvector I come up with here, though, is going to be a duplicate, a scalar multiple, linearly dependent on the eigenvector that I just came up with. I challenge you to try to come up with a linearly independent eigenvector. You won't be able to do it. So that would mean that our algebraic multiplicity, because we got a repeated root whose multiplicity was 2, that is not equal to our geometric multiplicity. We could not come up with 2 linearly independent eigenvectors. So keep in mind what we do with that situation is that we take our A minus lambda identity, or in this case, we plug in our lambda value. And we found by deriving this in class, if I take A minus lambda identity times x2, which I want to solve for, that eigenvector, and I set it equal to what I just found for x1, that equation right there will at least help me find an independent eigenvector. So I'm going to go ahead and take my A minus lambda matrix that I have from above, and I'm going to augment it instead with x1 to help me solve for x2. So I'm going to go ahead and plug in the negative 1, or I'm sorry, 1, negative 1 that I found here for my first eigenvector. Again, we derived in class Y. We can do that. That allows us to hopefully find a different solution. And this helps me a bit. This tells me that I can find an x1 plus x2 that would be equal to 1 instead of 0. So that's good. I'm going to go ahead then, and you could do this in a couple different ways, I'm sure here, because now I can actually use 0 for one of those values. I couldn't do that above because I couldn't get back to 0, but now I'm trying to get to 1. So I'm going to go ahead and use 1 for x1 and 0 for x2 to make that work, and that is linearly independent from the first eigenvector that I found. So let's go ahead and build our general solution here, and we could check that we get a fundamental set of solutions by finding the Wronskian and all of that. I won't do all of that, but my general solution, y of t, I'm going to take c1 times e to the lambda t, and my lambda, remember, was equal to 1, so c1 times e to the t, multiplied by that eigenvector x1, plus C2 times this whole big quantity. Remember, we have repeated. We have to do that special thing for Y2. So I have to take t, e to the t, times that first eigenvector, 1, -1, plus e to the t times my eigenvector that I found for x2. So 1, 0 that I did there. Okay. So I'll write that out. I'll just say this was x1 eigenvector that we used here and here. And then this was our x2. And again, in the notes that we did for 4.7 in class, I showed that full form of our solution there. So I'm going to skip to what we get for psi of t here, because you can multiply this out and verify that this is the case. But what we are going to get is e to the t and then negative e to the t for that first column. And then for our second column here, I'm going to go ahead and multiply out with all the stuff that's in the parentheses right here. I would get te to the t plus e to the t for this first element in column 2. And then I would get negative te to the t for the second element in column 2. And that works out with having that 0 in there, kind of shortens the work. But keep in mind that's getting multiplied by C1, C2, and we do want to solve for C1, C2. So remember the way in which we do that is we said, okay, I do have this, solution that says that if I have y of t, that it is equal to psi, my solution matrix, times c, my C1, C2 vector function there. And then in order to solve for C, I'm going to take my inverse of the psi matrix. So I'm going to take psi inverse, and we're going to make it easier for ourselves. We're going to evaluate at that initial value. In our case, it is 0 here. And we are going to multiply that on both sides. So I would have that multiplied by y of 0. And then that would give me my C values. Okay, so we're going to go ahead and evaluate psi at 0, and then we'll find the inverse of it. Psi of 0 gives me 1, -1. And then we get 1, plugging it into both these terms right here, because I have that t value right there. That's going to give me 0. And then I would get 0 for this last element. Now you can do this where you multiply it with our y of 0. Let me go back up and grab that. Our y of 0 there would be that 3, -1. Okay, so let me bring that down here. 3, -1. So I'm going to go ahead and invert my psi matrix here to find its inverse. And we do this after we've evaluated, so we're just dealing with constants here. And inverting that matrix, I would get 0, -1, and then 1, 1. The determinant on this psi matrix was just 1, so it makes it a little easier there to invert. You do have to remember the rule to inverting. With 2 by 2, it's obviously a little easier than 3 by 3, but that does make your job a little bit easier, because then if we're going to follow our rule here, we're taking the inverse of the psi matrix multiplied by our initial value matrix here. So I'm going to take this 0, -1, 1, 1, and I'm going to multiply that by 3, -1. And that would mean that for C, I am doing basically 0 plus 1 for that first element, and then it looks like I'm taking 3 minus 1 for my second element. So I would get my solution here 1, 2 for C1 and C2. Okay, so again, this means that C1 is equal to 1 and that C2 is equal to 2. Now, believe it or not, if you chose something different for that x2 eigenvector, we would get the same solution here at the very end for our particular solution. It makes sense. We want one particular solution. Obviously our general solution may look a little different, but we should be getting the same particular solution because we had the same initial value problem. All right, so plugging all that back in, here's y of t. If I am going to kind of leave it in this matrix form, I don't know. I wouldn't recommend leaving it in the matrix form because especially with having those initial values solved for, you are going to see most solutions where it's fully multiplied out. Okay, so I'm just going to go ahead and write it here. This is what we would be multiplying by our C matrix 1, 2. So typically you are going to see that full solution as e to the t plus 2t e to the t plus 2e to the t. Now, obviously, we can simplify by adding some like terms there, right? So you get 3e to the t. Well, that would be fine. And then I would get negative e to the t minus 2t e to the t. All right. So that is kind of our final answer right there. Again, obviously you can combine some like terms, but that is the general idea. Hopefully that helps. And let me know if you have any other questions with that.